This is the experimental setup for piezoelectric actuation for the delayed resonator on a half-inch steel plate. As you can see on the left, there is a delayed resonator setup with a piezoelectric actuator, and on top of which there is a counter mass, proof mass, and accelerometer, absolute accelerometer measurement, acceleration measurement setting. And on the other side of the plate, there is an excitation source, which is the same setup as the absorber itself, except that it does not have a measurement setting. And what we are trying to do is to excite the structure from this piezoelectric actuator point and absorb the oscillations at this point. Underneath the plate, there is another accelerometer which measures the displacement of the plate. Here is the second accelerometer underneath the absorber, and the claim here is that the accelerometer, this second accelerometer, is going to show zero trace once the absorption is in effect. This experimental setting is connected to the peripheral structure as shown. In the bottom you see the piezoelectric actuator drivers, amplifiers, filter circuits, and the oscilloscope. And actually the DSP card is located, the controller card is located in the host computer where the program development takes place. And we will be observing the traces of the primary system, that is the plate, and also the absorber here. What we are seeing is the traces on the top and the bottom. The top trace is really the reading from the primary absorber acceleration, and the bottom trace is the primary acceleration. And when we hit the starting, what will happen is the excitation from the excitation side disturbing the plate, and the absorber responding. And here it is. At 700 Hertz we see absorber response on the top, and in the bottom the plate is of course carrying a residual oscillation. And what the top numbers are at 703 Hertz, this is the excitation frequency, and also 330 millivolts or milli-Gs in acceleration of the bottom trace, peak-to-peak oscillations. That's what we would like to eliminate. Now, as soon as we hit the delay, this is the trace with no active control. That is, the passive absorption is in effect. Now we hit the active control in with delayed feedback, and the delayed resonator as calculated analytically is this. However, this is not a perfect absorption due to deteriorating conditions, obviously, or the nonlinearities involved. Then we have the auto-tuning algorithm that is built in. In every single keystroke, this absorption will be improved. And here it is, the first one, and the second one, and the third one, and it is pretty much set up. 5th, 6th, 7th keystrokes will basically do no further improvement. As you can see, it is about 11, 12 millivolts that is indicating the acceleration reading of the plate, which is probably nothing other than the quantization error and some reading errors, the sensing errors, and the noise involved. So this display is basically indicating full absorption at this particular frequency. The next, we will show that if we change the frequency from 703, it will change to another value, let's say 720, 740 Hertz, and the absorption will take effect automatically, and then we will show a sweep following that. We'll start the experimentation at 675 Hertz, and here it is, 675 Hertz, and the plate response is 410 milli-G range in the bottom, peak to peak. And when we trigger the delayed resonator, this is what happens. It is a reduction of approximately 70%, 75%, by analytical solutions, analytical feedback gains and delays. Now the further tuning, the first level, the second level, third level, as you can see, it is down to about noise level, and we claim that it is, the absorption is typically better than 40-45 decibel compared to the best tuned passive absorber. The excitation is at 675 Hertz, and then we will be going up in frequency. First, this is the passive absorption, and the delayed resonator hits, and the tuning takes place. Yeah, and now we will be varying the frequency at a certain pace we wish, and here it is, 680, is that right? 690, 700, 705, and as you see, the primary is not responding. It is not more than 20 milli-G of acceleration, which is an indication of better than 40 dB down from the passive absorption situation. And we can go up to about 775 before hitting the instability limit. Here it is 780, is that right? 785. Let's stop it here, that's fine. 750 Hertz this time, the excitation frequency, and there is no feedback, passive absorber. The delayed resonator kicks in, and here it is, and the tuning takes place in the next few steps, and there will be a tabulation of these to see for those of the viewers interested. But again, the most important thing is that peak-to-peak value is about 14 milli-G in the plate signal, plate acceleration, and that is for all practical purposes better than 40-45 dB down.